Pluto is a distant and mysterious dwarf planet, once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon? Or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact ***. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Neil deGrasse Tyson and Michio Kaku are both raising the red flag about a possible hazardous collision between these two planets that could pose a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets ***. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets ***. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and affect each other through gravity. It's akin to predicting their movements based on their initial positions and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way ***. The terms azimuthal libration and latitude libration, along with the VZLK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is azimuthal libration. In the context of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated significantly above their orbital plane, providing an additional layer of protection from potential collisions ***. Another crucial component in this equation is the VZLK oscillation, named after three scientists, von Zeipel, Leff, and Kai, who studied how objects move in space. This oscillation involves how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects their movements. In Pluto's case, the VZLK oscillation helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems erratic, this oscillation helps keep it moving smoothly over long periods. The VZLK oscillation demonstrates that even if things in space appear wild and random, some patterns and rules maintain order ***. All of these components help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or get thrown off course. The three-body problem aids in understanding how these paths change due to the gravitational pull of other objects. Studying this helps us learn about Pluto, our solar system, and distant worlds. Numerical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping chaos at bay. Recent computer tests have helped us understand how the giant planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun****. Neptune has a special connection with Pluto. For every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. But Neptune isn't the only one involved. Jupiter's gravity also plays a significant role in keeping Pluto's orbit safe and stable, and Saturn contributes a bit too. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for an incredibly long time, even billions of years. So it's like Neptune, Jupiter, and Saturn are all working together to make sure Pluto continues moving safely through space without running into trouble. These phenomena are essential in maintaining the order and predictability of celestial bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies, ***. For Pluto, especially with talks about it possibly crashing into Neptune in the future, understanding its orbit is essential. This provides a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability, ***. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term orbit. Using computer simulations has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use complex math to mimic how Pluto and other celestial bodies, like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even slight tweaks can make a big difference in where Pluto goes.
Back in the late 1980s, these simulations showed something interesting about Pluto's path. Even though it has mechanisms like azimuthal and latitude libration to keep it steady, its orbit can still be quite wild and unpredictable. If you start off with just a tiny difference in where Pluto is or how fast it's moving, its path can end up looking very different over many years. But despite all this chaos, Pluto's orbit remains stable for an incredibly long time, like billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it seems erratic at first, ***. Predicting cosmic events, especially when they involve chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numerical simulations provide powerful means to understand and anticipate the future positions of celestial bodies, they also highlight the limitations in our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight error or oversimplification can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto serves as a reminder of how much our knowledge still remains limited, ***. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune? despite all these complex forces trying to keep such an event from happening? Neil deGrasse Tyson, a prominent astrophysicist and a pivotal figure in popularizing astronomy, provides a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion but as a necessary adaptation to our growing understanding of the many bodies orbiting our sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a reminder of how much there is still to discover in space. The intrigue of these unknowns, according to Tyson, is what makes astronomy so captivating. Similarly, Michio Kaku, a prominent theoretical physicist and futurist, brings his unique insights into the conversation. Kaku often emphasizes the importance of understanding the larger cosmic picture and the potential implications of celestial events on Earth. His perspective on the possible collision between Pluto and Neptune serves as a cautionary reminder of the ever-present forces at play in the universe. Kaku's focus on the gravitational dynamics and their potential consequences resonates with the wider public interest in space and the unknown. He urges for continued exploration and understanding of our solar system, highlighting the necessity of investigating these cosmic mysteries to prepare for potential future events. The implications of a collision between Pluto and Neptune raise numerous questions about the broader dynamics of our solar system and the potential consequences for Earth. While a direct impact may seem remote given the current stability of their orbits, the mere notion of such an event invites curiosity and concern about the fragility of celestial order. The concept of celestial mechanics is intricate, but it ultimately highlights the delicate balance that exists in space. Understanding these dynamics helps us appreciate the wonder of our solar system and the profound mysteries it still holds. Whether one views Pluto as a planet or a dwarf planet, its story is deeply intertwined with the broader narrative of cosmic exploration and discovery. As we continue to explore the cosmos and uncover its secrets, the enigmatic nature of Pluto and its complex orbit will undoubtedly remain a topic of fascination for scientists and enthusiasts alike. In conclusion, the potential collision between Pluto and Neptune serves as a powerful reminder of the complexities of celestial mechanics and the delicate balance that governs the movements of bodies within our solar system. With prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku raising awareness about this topic, the intrigue surrounding Pluto continues to captivate the public's imagination. As we look toward the future, understanding Pluto's orbit and its relationship with other celestial bodies will be key in unraveling the mysteries of the cosmos. Through continued exploration and study, we may yet uncover new dimensions of knowledge that deepen our understanding of the universe and our place within it. As we dive deeper into the mechanics of Pluto's orbit, it's essential to highlight the historical context surrounding its classification and the implications of its orbit on our understanding of the solar system. Initially discovered in 1930, Pluto was celebrated as the 9th planet. However, this classification was contentious, given the discovery of other trans-Neptunian objects that share similar characteristics with Pluto. The reclassification of Pluto in 2006 by the International Astronomical Union, IAU, ignited debates within the scientific community and the public alike. Many viewed this demotion as an insult to Pluto's storied legacy. This discourse underscores not just Pluto's physical attributes, but also how human perception and scientific understanding evolve in tandem. As more celestial bodies are discovered, particularly in the Kuiper Belt, our definitions of planets and other celestial classifications have been challenged. Furthermore, the dynamics between Pluto and Neptune offer an excellent case study in gravitational interactions. These forces shape not only their respective orbits, but also the behavior of many other celestial bodies in their vicinity. The gravitational influence of giant planets like Jupiter and Saturn extends far beyond their immediate neighbors. These interactions can lead to what is known as resonance, a situation where two orbiting bodies exert a regular, periodic gravitational influence on each other, often stabilizing their orbits. For instance, the resonance between Pluto and Neptune is not merely a byproduct of their respective orbits, it's a protective mechanism. This gravitational dance prevents close encounters that could destabilize their trajectories, thus mitigating the risk of collision. The intricate relationships within our solar system emphasize how interconnected celestial bodies are, each affecting the others in subtle yet profound ways.
To further explore the implications of a potential collision scenario, we must consider the sheer scale of the solar system. The distances involved are astronomical. Even a slight alteration in orbit can lead to drastically different long-term outcomes. While the possibility of a collision between Pluto and Neptune remains low due to their current orbital stability, the gravitational interactions of other celestial bodies introduce a degree of unpredictability that warrants ongoing observation. Scientific advancements, particularly in the realm of computational astrophysics, enable astronomers to simulate and predict these complex orbital dynamics. Researchers utilize advanced algorithms and modeling techniques to visualize potential future scenarios. By feeding in various initial conditions, they can explore a range of outcomes, providing insights into the stability of celestial orbits over time. The exploration of Pluto's orbit also invites broader philosophical questions about our place in the universe. Understanding these distant worlds serves as a reminder of our planet's fragility and the transient nature of celestial bodies. As we continue to study Pluto and its unique characteristics, we gain not just knowledge about one dwarf planet, but also a deeper appreciation for the complexities of the cosmos that surrounds us. In essence, the case of Pluto illustrates the importance of continual learning and adaptation in the scientific community. As our methods of observation improve and our understanding deepens, we can better predict the behaviors of celestial bodies and perhaps one day unveil the mysteries that remain in our solar system.